Welcome back to part 2 of the O-level chemistry lecture series on organic chemistry. So earlier in the part 1 of the video we covered alkanes and alkenes. So part 2 we will cover alcohols, carboxylic acids and a little bit more. So like alkanes, this structure you see here is called the functional group. So the functional group is a small group of atoms which together gives the chemical properties of the class of substances. So in this case, alcohols, this is the OH group. We call this the hydroxyl group. Okay, hydroxyl group. So the question asks you, what is the functional group of alcohols? You will draw the OH out with a dash, like this, and then you will say this is the hydroxyl group. So like alkanes and like alkenes, alcohols also form a homologous series, and the general formula is CnH2n plus 1 OH, hydroxyl functional group. So every subsequent molecule increases by a CH2 homologous series. Okay, there are various ways to represent the structural formula for alcohols. Sometimes you may see this, sometimes you may see this. They are both the same. They're both the same. For O levels, it is more often that you will see this. Right? So this is basically all the atoms, most of the atoms actually combined, condensed together. So CnH2n plus 1 OH. This is the structure. This is the general formula for alcohols. Because of the OH group here, alcohols actually exhibit some unique properties. Later on we will see a little bit more. So how do we get the alcohol in the first place? There are two ways to get alcohol: fermentation and steam addition to alkenes. So recall this was from the earlier topic of alkenes. When you add steam to an alkene, you get the alcohol. In this case, let's make ethanol. So how do we make ethanol? From fermentation and from steam addition. So let's start with fermentation first. So to ferment something, you must start off with a sugar. In this case, this sugar is called glucose, C6H12O6. You need yeast. You need a nice warm temperature of 37 degrees Celsius, and you must have no oxygen present. Okay, so during this fermentation process, you will get the alcohol here, ethanol. You will only get ethanol from fermentation, and you will have carbon dioxide. Okay, so this process is actually used to raise the dough in making bread. So why is your bread nice and puffy and fluffy? It's because when the dough is made, the dough is actually flat. In the dough, they mix in yeast. So in the oven, the fermentation process happens. Ethanol is produced. Ethanol boils at about 78 degrees. So actually, it evaporates off in the oven. So it is gone. Carbon dioxide is also formed, and this carbon dioxide actually raises the dough out to give you a puffy, fluffy bread. Right? So glucose gives you ethanol and carbon dioxide in the presence of yeast, 37 degrees Celsius, and the absence of oxygen. So this is a common setup in the lab used to do simple fermentation. Take note, everything is sealed. Everything is sealed here to prevent oxygen from going in. And if I were to insert a test tube with lime water here and a bubble, I will be able to see white precipitate. Why? Because carbon dioxide is released during the fermentation process. Okay, so there's some things to take note of for this process. Make sure it's 37 degrees Celsius because yeast contain enzymes. Enzymes, they work at an optimum temperature, and this optimum temperature is 37 degrees Celsius. No oxygen is present, because if oxygen is present, first of all, ethanol is not produced. Why? Because the process of producing ethanol by the yeast is actually called anaerobic respiration. So this reaction actually takes place only when there's no oxygen present. So when oxygen is present, the yeast undergoes aerobic respiration. During aerobic respiration, carbon dioxide and water is produced. You don't get your ethanol. Okay? And if oxygen is present as well, ethanol can actually be oxidized into ethanoic acid, and we don't get ethanol at the end of the day. And last but not least, the solution of the ethanol form is only about 15 to 18% concentrated. Why? Because as you increase the concentration of ethanol, the yeast actually dies. And if it dies, nothing can happen. Fermentation will stop. So in the lab, for clean rooms, before they do bacterial cultures, they actually spray ethanol on the surfaces and then they wipe the surfaces clean. So the ethanol kills the bacteria, kills the fungus, and kills everything on the surface to make it sterile. So if you have too much ethanol during the reaction, the yeast will actually die. When the yeast dies, no reaction takes place. Okay, and this we mentioned earlier, we will see white precipitate in the lime water because carbon dioxide is formed during the fermentation reaction. Next part is ethene with steam. We covered this earlier already, so just do a quick recap. Basically, you have your steam, you have your phosphoric acid, 300 degrees Celsius, and your 60 atmosphere pressure. You add the H2O across the double bond, and we have the alcohol. Properties wise, physical properties are slightly different from that of alkanes and alkenes. So alkenes contain only carbon and hydrogens. So predominant force between such molecules is van der Waals forces. But for alcohols, they have the hydroxyl group. So there's actually one more force which is involved. It is not in syllabus, but I'll just briefly mention this. It is called hydrogen bonds. So on top of van der Waals forces, it has hydrogen bonds. So there's van der Waals and there's hydrogen bonds present. Both are present. So as a result, they exhibit slightly different properties. First of all, boiling point. Notice that the alcohols are liquids at room temperatures, even for the 1 carbon alcohol, methanol. It is already a liquid at room temperature. Why? Because the hydrogen bonds are actually pretty strong, so it prevents the molecules from vaporizing at room temperature. But likewise, similar trend to alkanes, alkenes, as the number of carbon atoms increases, the boiling point will increase. Why? Because the strength of the intermolecular forces will increase. Okay, the strength of the intermolecular forces will increase. Take note, I do not say that the strength of the van der Waals forces between the molecules increases, because earlier I mentioned that between alcohols, there's van der Waals forces and there is hydrogen bonds. So it is not just the van der Waals forces. It's not just the van der Waals force strength depends on the MR. Hydrogen bond strength largely remains about the same. So if I were to say increasing strength of van der Waals forces and hydrogen bonds, this is a wrong statement because only this increases. This one stays about the same. So to be safe, we condense this whole thing into intermolecular forces. So we simply say that the strength of the intermolecular forces increases as the MR increases. Hence, the boiling point increases because more energy is required to overcome the intermolecular forces. Okay, so we condense these two forces together into intermolecular forces of attraction. Solubility wise, alcohols are soluble in water. Short chains more soluble. The longer chain ones are not as soluble. So for example, your alcoholic drinks, vodka is almost 40% ethanol. You see a clear solution. You don't see two layers in the thing. You see one single solution complete. Why? Because the ethanol inside dissolves completely in water. Chemical properties for alcohols, partly similar to alkanes, alkenes, and because of the hydroxyl group, you get two more special reactions here. So we do the first one first, combustion. Like all hydrocarbons, when you burn something, you get CO2 plus water. Even though this is alcohol, this is not a hydrocarbon, but you still get the same products, carbon dioxide and water. Okay? It burns cleanly with a pale blue flame. It burns really cleanly. Completely, you have CO2, water. Incomplete, carbon monoxide, soot, and water. And this is an exothermic reaction. When it burns, it releases energy into the surroundings. Exothermic reaction. Okay, the next reaction, oxidation. This is a new reaction which is only possible because of the hydroxyl group here. So what happens? During this reaction, the alcohol is oxidized into an acid. This is the functional group of carboxylic acids. We will cover more on acids in the later part of this topic. So bear with me now first. just take the COOH as carboxylic acid first. So during the oxidation reaction, what happens is the alcohol, notice oxidation, it adds oxygen in, and it forms the acid. What do you need? You need dilute potassium manganate 7 and H2SO4. So this is what we call acidified potassium manganate 7, you recall? Okay, the acidified potassium manganate 7, and we need some heat. Basically just some slight warming. So during this reaction, something special happens. Okay, something special happens. Potassium manganate is purple in color, right? So redox involves one reduction and one oxidation. So if my ethanol is oxidized into ethanoic acid, this oxidized, something must be reduced. So what is reduced? It is the manganate ion, MnO4 minus. It is reduced to Mn2 plus. So this is purple in color. This is pinkish, more towards colorless. So at the end of the day, you will see the solution change color from purple to colorless. So when it is colorless, you know that the reaction is probably complete and you have your ethanoic acid. The next reaction which we are going to talk about is esterification. It's a little bit similar to, it's something like combining two molecules together. It's a complicated name for a very simple reaction. The product at the end of the day is called an ester. That's why it is called esterification. Esters are actually found in many places. For example, perfumes. They are sweet smelling. That's why they are used in perfumes. Sometimes esters can be found in food as well to give you the very sweet, nice smell of certain foodstuffs. For example, candies. We will cover more on esterification after we cover carboxylic acids, because there is a chemical reaction which you will need to learn how to draw, and you can only do so after we cover the carboxylic acid topic. So for now, we will move on from here into the checkpoint. You can pause the video now to attempt the checkpoint. Checkpoint 3. We have 4 organic molecules here, PQRS, which two members are the same homologous series. So homologous series, they differ from the next member by a CH2. So if we take a look around, we have this and we have this. Homologous series must be molecules of the same class of compounds. So if we take a look here, this is the alcohol, this is the alcohol. These two are not the same. Okay, they are not the same. P and R is not the same. P and S, they are the same. OH, hydroxyl group. OH, hydroxyl group. So even though R has a O here, it is not an alcohol because it doesn't have the OH group or the hydroxyl group. Okay, so homologous series, same class of compounds, but they vary by a CH2. So the answers are P and S. What happens to the boiling points as the number of carbon atom increases, or as N increases? So as number of carbon atoms increases, you have stronger van der Waals forces between the molecules, which means you need more energy to overcome them, so your boiling point will increase. So we look for the graph which shows an increasing trend. Answer is A. The following tests were done on two colorless liquids. Shake with bromine water, decolorizes, it means this must be an alkene. Heat with potassium manganate 7, acidified potassium manganate 7 remains purple in color. It remains purple in color. So if you recall what reactions you have learned before, this is for the oxidation of alcohols into carboxylic acids. So if it remains purple in color, liquid X is most likely not an alcohol. Liquid Y shared with bromine water remains reddish brown, so this is an alkane most likely. But it decolorizes acidified potassium manganate, which means this is, instead of alkane, we can say that this has no double bonds. No double bond. It decolorizes, it contains a hydroxyl group. So this is alcohol, so liquid Y is an alcohol. Liquid X is a alkene. It's an alkene. So which one is an alkene? Alkene is this one. There's an alkene here. There's an alkene here. Liquid X remains purple. Liquid Y decolorizes. So liquid Y is the alcohol. So answer is B. Okay. Which compound has an addition reaction with chlorine? So addition reaction, you must remember straight away. Addition means you must add across a double bond, which means that the compound must be what? It must be a alkene. Okay, addition reaction. Straight away, double bond. Double bond means must be an alkene. Alkene general formula CnH2n. So if you look across, which one could it be? It is number A, C2H4 or ethene. This is an alkane. Alkanes do not undergo addition reaction with chlorine, undergoes substitution reactions. These two, nope. Alcohol, acid, nope. Which now brings us to the last class of organic compounds, carboxylic acids. So once again, this COOH here is a functional group of carboxylic acids. Functional group. And it gives it its properties. We call this the carboxyl group. Okay, we call this the carboxyl group of carboxylic acid. So for example, if I were to write this CH3COOH, this is a carboxylic acid because there's the COOH here. Just for information, the bombardier beetle actually squirts out acid spray when it meets danger. Okay, when it is in danger, it sprays out acids to try to ward off its predators. Alright, so like alkanes, alkenes, and alcohols, carboxylic acids also form a homologous series. So they differ from each one by a CH2, and they contain the carboxyl group. They contain the carboxyl functional group, and they have the general formula CnH2n plus 1 COOH. Take very special note of this because one of the carbons is actually in the carboxyl group. So this is a common source of error for students because if I were to draw this, if you are not careful, you may think that this is the one carbon carboxylic acid, but this is not true. This is actually the 2 carbon carboxylic acid. There are two carbons here. So take very special note. This is one carbon. This is one carbon. These are 2 carbons, and this is 3 carbons. Okay, so take very special note of this one. First one is called methanoic acid, second one ethanoic acid, third one is called propanoic acid, so and so forth. And how do they behave? Physical properties similar to alcohols. Chemical properties similar to acids because they are acids. So boiling point, like all the rest of the organic molecules you have learned, it increases as the MR increases. Why? Because you need more energy to overcome the stronger intermolecular forces between the molecules. Solubility wise, only the first bit are soluble, like alcohols. The rest are insoluble. Now, this is the interesting part, chemical properties of carboxylic acids. So based on the name itself, you should already know that it should have acidic properties. That's why it is called an acid. The next reaction is esterification, which we skipped earlier because we haven't covered acids yet. We will cover this in detail later on. So carboxylic acids are actually weak acids. They are weak acids. So if you remember the definition of weak acids, it means that they are partially dissociated. They are partially dissociated in the presence of water. Okay? So in the presence of water, they are partially dissociated to give you the H plus ion. This H plus ion gives rise to the acidic properties of the carboxylic acids. So if I draw HCl here, it gives me H plus Cl minus. This is a complete dissociation to give me my H plus ions in aqueous solutions. So likewise, if I have an H plus for my carboxyl functional group, this compound can similarly exhibit acidic properties, which means that it will turn blue litmus paper red it can react with relatively reactive metals to give me salt and hydrogen gas. So this equation here looks complicated, but actually it is quite simple. So let's take a look. If I were to do a similar reaction, Mg plus HCl, okay, I would write acid plus metal gives me salt and hydrogen gas, right? Okay, so if I were to convert this into my ethanoic acid, I know that this H is dissociated as H plus, and this part here would be the other part of the ion. So if I were to convert this part, if I were to write this, if I were to convert my COOH minus, and let me treat it as X minus, I will have my Mg X2 plus H2, and then I balance, right? So if I replace my X with this one, CH3COO, I need 2 of this, and Mg, I have the complete formula. Okay, so when you write an equation involving a carboxylic acid, in your mind, if you cannot write it out, in your mind, replace the acid with HCl or HX, write the reaction as per normal, and then convert the ion into the anion from the carboxylic acid molecule. Alright, the writing for carboxylic acid equations is a bit different. You put the metal ion at the back versus this one where you put the metal ion at the front, right? So you put the metal ion at the back of the formula. So we have this magnesium ethanoate. So this is called magnesium ethanoate. So ethanoic acid, I get ethanoate. Erase this. Ethanoate. Okay, so if I have methanoic acid, I will have methanoate. Just replace the OIC at the back with OATE. Okay? So like other acids, carboxylic acids can also react with carbonates, and I'll get a salt, water, and carbon dioxide, which means that I will see effervescence. I can test for the gas with lime water. I will have a white precipitate, and it will undergo neutralization reactions. Acid and base gives me salt and water. So this is the salt, sodium ethanoate. Which now brings me to esterification. So basically, when a carboxylic acid reacts with an alcohol, it gives me an ester. Ester, as I mentioned earlier, is a sweet-smelling colorless liquid. Sometimes it is insoluble in water. Over here, I have a simple esterification reaction. This is the alcohol, ethanol, and this is the acid, ethanoic acid. Notice they all come together to give me a larger molecule and water. So let me decipher this equation step by step. Okay, so if you take a look here, the water actually comes from the H of the alcohol and the OH of the acid. So over at this molecule here, if you take a look, the CO part here is over here, which means that this part here is actually from my acid, and this part here is from my alcohol. Okay, take very special note. The COO here doesn't all come from the acid. The CO here comes from the alcohol. The CO here comes from the acid. Be very careful, because later on when you write the formula out, you may be asked to draw backwards. And if you see wrongly, you may get the wrong acid and the wrong alcohol components. So let's go into a little bit more here. This ester here, once you see COO, which is not at the end, COO bonds carbon and bonds carbon, you must straight away think that this is an ester. Okay, so how do we split the ester into half? We split it at the COO portion. So this CO portion here belongs to the acid. So this is the acid part. This part here belongs to the alcohol. So this is the alcohol part. Alright? And when we name it, we name the alcohol in front first. So this is from ethanol. So ethanol, I will call it ethyl. This part here comes from the acid. It comes from carboxylic acid. So if I draw this way, I will have this carboxylic acid, which is called ethanoic acid. So ethanoic acid, I will call ethanoate. So this ester is called ethyl ethanoate. Alcohol in front, the acid part behind. Okay, but when I write the formula, it is the opposite way. CH3COO CH2CH3. So if I split, see I split this here. So if I split this here, the CO belongs to the acid, which means that this portion here is now the alcohol. Okay, so take very special note, it is opposite. CH3CO acid portion, this portion here is the alcohol written in reverse. OCH2CH3, or you can write CH3COO C2H5. Both ways are acceptable. Both ways are acceptable. Okay, this one is a bit confusing, so take special note, rewind the video, watch again to make sure you're very clear about this area. Okay, checkpoint 4, first question actually helps you revise a little bit more on naming the ester properly. So let's move on to checkpoint 4. You can pause the video now to attempt checkpoint 4, continue when you are done. So the first compound for checkpoint 4 here, you have the alcohol and you have the acid. So remember naming alcohol is in front, acid is behind. When you write the formula, the acid is in front, the alcohol is behind. So the first one is ethyl methanoate. Ethyl methanoate. Formula wise, if you can't write it out straight away, always draw it out. So we draw the acid first, methanoic acid. This is methanoic acid. Oops. Methanoic acid has one carbon. So this is methanoic acid. And this is ethanol. Okay, so when they come together, this portion combines with this portion. So if I were to draw this out, this is the acid portion. And I am now drawing the alcohol portion. Notice, take a very close look at how I draw. I'm now drawing it backwards because this COO portion tells me that this is the ester. So my O is here. Next one is carbon. From my O, the next one is carbon. From my carbon, the next one is another carbon. And my carbons have 5 hydrogens. So this is the structure of my ester, ethyl methanoate. So when I write the formula out, it is actually H COO CH2 CH3 or C2H5. Okay. Next one, ethanol propanoic acid. So it will be ethyl ethanoate. Structure is as such. CH3COO CH2 CH3. So how do we get this structure? Ethanoic acid is like this. Ethanol is like this. So my acid portion combines with my alcohol portion together to give me my ethyl ethanoate. So this is my acid portion and this is my alcohol portion. Oxygen, carbon, carbon, oxygen, carbon, carbon. and then H. So writing formula CH3 COO C2H5. Okay. Last one, ethanol and propanoic acid. You'll get me ethyl propanoate formula as such. So how do we get this structure? Draw the thing out and then combine together. If you can't write this out straight away, do not try to write it out straight away. Otherwise, most likely you will get it wrong. Okay, draw it out first and then convert the structure into the formula. Question number 2, you have a series of tests done on compound X as shown. You add bromine water, turns colorless. It means that there is a double bond present, at least one double bond present. You add aqueous sodium carbonate and you see carbon dioxide. So this is a carbonate, so acid carbonate, you get carbon dioxide. So there must be a carboxyl group present. So look for the compound with a carboxyl group and a double bond. And the answer will be D. Okay. Next part. Question 3, 10 cm cube sample of gaseous hydrocarbon was completely burned in oxygen. Total volume of products was 70 cm cube. So which one represents the combustion reaction? If you recall from mole concept, gases can be counted directly from the volumes. So which one do you have? 10 cm cube of hydrocarbon giving you 70 cm cube in total of gases. It is answer number C. So we have 1, 3 and 4, which means it is 10 cm cube, 30 cm cube, 40 cm cube. So 10 cm cube gives me 70 cm cube in all. Alright, so after we cover some of the reactions of ethanoic acid, we now move on to how ethanoic acid can be produced. One of the reactions was covered earlier already. This one is a new one. So we can oxidize ethanol to ethanoic acid by using acidified KMnO4 and heat. In fact, this was covered under the topic of alcohols, and this one was covered under fermentation, right? So first one, oxidation of alcohol to acid using my oxidizing agent. Second one is fermentation. Oh, sorry, not fermentation. This is oxidation as well. So the ethanol could be produced from fermentation, oxidized by oxygen in air to give me ethanoic acid. This is a slow reaction. This is a fast reaction. Now let's try checkpoint 5, which consolidates the first 4 topics. And you can pause the video here, continue when you are done. Alright, checkpoint 5. Write the chemical equation for the reaction between dilute ethanoic acid and potassium carbonate. So this is a carbonate acid reaction. It will give you salt, water and carbon dioxide. Okay, salt, water and carbon dioxide. Acid, carbonate reaction. So like earlier, if you can't write this out properly, you can't write it based on the ethanoic acid here. Very easy. Do it this way. Convert your ethanoic acid into HX first. HX, X represents this portion, and then you just write the equation. HX or even HCl plus K2CO3 gives you KX plus H2O plus CO2. Then you balance the equation. Okay, balance the equation. So once it is balanced, now you can convert the X into your CH3COO. So what we have is 2 CH3COO plus K2CO3 gives me 2. Remember, for carboxylic acid equations, it is written the other way around. 2 CH3COOK plus H2O plus CO2. And there you have it, the balanced chemical equation for the acid carbonate reaction. Next one is a simple one, acid with metal. So acid metal reaction, you get salt and hydrogen gas. How do we test for the gas? You should know it extinguishes a lighted splint with a pop sound. Alright. Now we move on to the last topic of organic chemistry, which is macromolecules. We will go on to this in the third part of the organic chemistry lecture series videos. So catch the part 3 of the videos for macromolecules.